Hello, my name is Ben Consalvo and I will be presenting on deep learning for salt body detection, a practical approach. I am very excited to present to you some of the work I completed at Fairfield Geotechnologies in conjunction with Icon Science. I know there is a lot of hype about machine learning and deep learning these days, but in this case I really do believe that there is significant reason to consider using deep learning to make interpretation workflows much more efficient. So the agenda for today will be first to understand the problem of salt detection. Number two, to look at briefly at the machine learning methods that I used. And then the bulk of the talk will be spent in number three and number four, looking at two case studies from the Gulf of Mexico where the method was applied. Though both are from the Gulf of Mexico, the salt bodies in these studies have very different character and extents, and we treat each survey as its own machine learning and prediction study. We found that relatively little manual data labeling are required for the algorithm to learn what the salt looks like. Number five, I'll briefly show you a tool I wrote to convert the machine learning output of volume to horizons. And finally, I'll go through my conclusions. So in this talk, I will use the terms deep learning and machine learning interchangeably, even though I understand that deep learning is a subdiscipline of machine learning. So to give us some context for this problem, salt interpretation for a single seismic interpretation project can take months to complete, and so it's very time consuming. And second, the accuracy of the salt boundary is crucial. It's required for subsalt imaging and for subsequent drilling of oil and gas. So the goal of this study was to use machine learning techniques to automatically predict the location of salt bodies, specifically to obtain highly accurate salt predictions, so 95% or better accuracy, and to reduce salt interpretation turnaround time to days or better. So I have to ask the question at the beginning, is it worth its salt? And the reported accuracy rates for this approach are 98% and higher. So we have very good accuracy rates as compared to the human picks for salt. So deep learning and neural networks are used to learn and predict the locations of salt. The training data consist of some kind of seismic image and the associated location of salt for that image. The three main convolutional neural network architectures that were tested were a 2D and a 3D patch-based convolutional neural network, and the third one is this adaptive 2D unit. The first two approaches use a similar concept of feeding many small patches, so these small patches, into the CNN. For example, a whole image might actually be 1465 by 1601 pixels, but we feed many 128 by 128 overlapping patches that could be extracted for training. After Ronneberger et al. 2015, we designed a third adaptive unit architecture. The adaptive term just means that our neural network can receive any size of image as input and produce that same size as output for the salt mask. Unlike the patch-based networks, the adaptive unit can take an entire inline image, so you can see here on the left, we're inputting an entire image rather than just the patches. Both the patch-based and unit-based methods use convolutional layers, dropouts, max pooling layers. Two key differences with the unit approach as compared to the patch-based approaches is that number one, the prior convolutional blocks actually directly inform the later convolutional blocks here, and the second is that the entire context of the whole inline image are used, whereas only small patches are used in the patch-based approach. Overall, the purpose of the neural network is to abstract and learn the relationship between the pixels, and that's mainly accomplished by these convolutional layers. So the first case study and application of the method is an offshore seismic survey called Julia. A few details about the Julia survey are that it's about 11 miles by 11 miles. It's located 264 miles southwest of the city of New Orleans in the Gulf of Mexico. It's a survey of 1405 inlines and 1465 crosslines. And the water depths here are fairly deep at around 7,000 feet. The salt bodies are quite large in this area. It can be up to 3.1 miles thick. Here are top-down views of the top of salt for the Julia survey. So the left image is the manual pics of the top of salt horizon. So that were done, over weeks to pick the top of salt in the whole survey. And the right image is a top-down view of the machine learning picked top of salt, and this is in orange. So as you can see, the machine learning approach has predicted the salt with a very high accuracy as compared to the human picks. You may have been wondering which of the methods I mentioned earlier performed the best for picking salt. We found that the UNet approach far outperformed in both speed and accuracy compared to the 2D and 3D patch-based approaches. The machine learning picks here are displayed in purple, so the volume output, and then here in red you can see the manual top of salt picks. So though the UNet isn't perfect in its prediction, it outperformed the 2D and 3D CNN approaches significantly with very little training. So you can see here there are some missing patches in the 2D and 3D patch-based approaches, whereas with the UNet approach it's done a very accurate job and very quickly. So as I pointed out, the adaptive UNet approach came out on top. So looking at some of the training details for the Julia survey, the image I'm showing here shows again the manual salt picks in red and the machine learning picks in purple. And the depth extent of this survey is about 5 miles, and as I pointed out before, the length in one of the directions is around 11 miles. One of the incredible things we found with the UNet approach is that we actually only needed to provide 5 randomly picked inlines and their associated salt picks out of a total of 1405 inlines to properly train the network and accurately pick the salt for this survey. One of the benefits of using the Julia survey is that the salt to sediment ratio, or salt to no salt ratio, was about 50%. As you can see on this image, it looks like around 50% of the image is occupied with salt. And this is great for a binary classifier that you're trying to teach. So we trained with 5 inlines, and we used 2 inlines for validation and 1 inline for test. And we achieved an overall accuracy of around 99% when measuring against the human picked salt over the whole 3D volume of 1405 inlines. Here's an example inline again of the machine learning picks in purple and the manual picks in red. So a very satisfying result, as even some of these small inclusions the machine learning prediction was able to find. Here's another example of quite a complicated salt structure with overhangs and inclusions. Again, I'm quite happy with the overall result, even though the machine learning prediction is not perfect. Any time can save on manual salt picking is helpful. For the Julia training, here I'm showing final training and validation loss on the left, and my accuracy curves on the right. The desired result is that training loss and validation loss would go down, would decrease, and that the accuracy would of course increase with more time or more epochs. The validation accuracy, you can see, does bounce around up and down, but remember that only 2 inlines were used during the validation process, and with such little data for validation, it isn't so abnormal for this curve to bounce up and down. And we did, as I pointed out at the top here, we picked the lowest validation loss for our model, so it didn't really have an impact on the model that we ended up using for prediction. The overall results for Julia are as follows. So the manual picking of around 5 inlines takes 20 minutes. The training on these 5 inlines on an NVIDIA Tesla V100 GPU takes around 11 minutes. The prediction on the entire 3D volume only takes 3 minutes on the GPU or 48 minutes on the CPU. So the total manual picking time plus machine learning time is about 1 hour. If we compare the total time of 1 hour to 3 weeks of manual time to pick the whole survey, a clear business case can be made for using deep learning with only 1 GPU. Moving on to our second case study, is also an offshore field in the Gulf of Mexico, as I mentioned, called OGO. The OGO 3D seismic survey has a larger footprint than Julia at 25 by 29 miles, and it's located 140 miles southwest of New Orleans in the Gulf of Mexico, and it was recorded on 1900 inlines and 1640 crosslines. The water depths are much shallower than at Julia, at only around 50 meters or 160 feet. The salt bodies are much smaller, more dispersed, and only around 3,000 feet thick. The first image here is manually picked salt horizons, or the ground truth. The depth of the seismic extent is around 30,000 feet, or 5.7 miles. As I pointed out, and as you can see here, the salt bodies are much smaller and dispersed as compared to the Julia survey. This slide shows the same view, but with the machine learning picks at OGO instead of the manual picks. If I flip back and forth, you can see that the results are very comparable, and the machine learning has done a good job of predicting the salt as measured against the human picks. On the OGO dataset, more training data were needed for the network to understand what salt looked like. As you can see from the image here, the salt covers more like 10 to 20% of the image rather than 50% as in Julia. So in order for the network to learn about what salt looks like at OGO, it needed to have more inlines than Julia because of the smaller salt to sediment ratio. So in this case, we used, as I mentioned, 45 inlines for training data, 15 inlines for validation, and 16 inlines for test data. And to predict on the entire 3D volume of 1900 inlines, we achieved accuracy rates of almost 100% overall, 97% for salt, and 100% for not salt or sediment. Here's an example of the machine learning prediction in action. An example inline where the machine learning predicted salt very accurately. So again, machine learning in purple and the human pick in red. Even though the character and shape of the salt might seem quite pathological, the adaptive UNet architecture has learned the relationship between pixels to understand the difference between salt and sediment. Here's another example inline of picked salt between machine learning and human picked salt. Again, an excellent example of the machine learning method working. Here I'm again showing the loss and accuracy curves, but for the OGO dataset. The left plot, again, is loss versus epoch. The right plot is accuracy versus epoch. The training and validation data do track closely, as you can see, showing that the model is not overfitting on the training set. There are also a lot less big bumps in the validation curve that we saw in the Julia training, with one notable exception. But the reason for the smoother curve in this case is likely because more validation data were used, so 15 inlines instead of only 2. Again, we picked the best model on lowest validation loss. The manual picking time for the OGO survey took around 2 to 3 hours, a little bit longer, a few more lines than the Julia survey. The training took 74 minutes, or just over an hour, on the same GPU. Prediction, again, very fast, only 3 minutes for the entire 3D survey of 1900 inlines. And the total manual picking plus the machine learning time is around 4 hours. Again, if we compare the total time of 4 hours to 3 to 4 weeks, that would be taken of manual time it is clear that the deep learning has potential to save a lot of time in the salt picking interpretation workflow. Now that we have this output from machine learning, it comes out in the form of a mask of 1s for salt and 0s for sediment. However, it is easier in most modern interpretation packages to work with horizons or boundaries rather than a mask of 1s and 0s. So I just developed a small tool in Python that transforms the mask output to horizons for interpretation packages. I also added the ability to optionally remove small holes and inclusions that are output by the machine learning, because the horizons can become very multi-valued in Z and become needlessly complicated. The conclusions for today's talk. So the adaptive UNet approach produces pixel-to-pixel accuracies of 97 to 99% of salt picks, comparing the machine learning picks to the human picks in hours, and instead of 2 to 3 weeks of manually interpreting the same data. Some surveys do require more inlines of training if the salt-sediment ratio is small, as we saw with the OGO dataset. We had less salt to sediment. And I also showed that I produced a segmentation volume to horizon tool for interpreters, so to make it simpler, rather than using a mask of 1s and 0s, converted that to boundaries and horizons. So some of the next steps that would be great to take are testing on a real-world salt building scenario. So in the real world, we build top of salt 1, we flood the velocity with that salt velocity, and then we do a reverse time migration. Then we pick a bottom of salt, do another reverse time migration, etc. And so the idea here would be, at each picking of salt, we would apply this method, maybe just picking a handful of inlines or cross lines, and then letting the machine learning predict the rest. Another thing would be to possibly obtain a more generalized model to predict in any salt environment. And another great thing is PyTorch has released this 3D deep learning package, and that could really help in our 3D world. Thank you very much for your time. I hope you learned something today. I've left my contact here if you would like to reach out to me for anything. Thank you.